Well, good evening, AP Physics students. Welcome to your problem for today. Today we are going to truly enter another dimension of problem solving. And of course, by another dimension, I mean the third dimension. A unit on vectors wouldn't be complete without talking about all three dimensions, x, y, and z. Because after all, that's how the world we live in works. Or at least according to Isaac Newton, that's how it works. You know, Einstein thinks 4 dimension, string theory's like, oh, it's 10 dimensions. But anyway, 3 dimensions. Let's talk about it. So in problem number 55, we're told to throw down an axes here, x, y, west, east, north, south. And we are told that there's a plumber who comes out of his truck and walks 25 meters to the east. Okay, so far so good. Then the plumber walks, he does not walk 25 meters to the east. He walks 50 meters to the east. And then he walks 25 meters to the south in this building. And then the plumber has to go to the basement, so he goes 10 meters down, right? And how do I draw going 10 meters down, straight down from right there? Well, there's some programs on the internet that do a pretty good job of drawing in 3 dimensions, but I am not like one of them. So I am just going to think in my head, okay, from there he goes straight down 10 meters. So if I were to call the overall displacement of the plumber vector D would have x, y, and z components, okay? And that's what the problem asks for. For components, I think we could do this, right? What would the x component of this vector be? Well, that would be a plus 50 meters. What would the y component of this vector be? Well, that would be a minus 25 meters. And if we zoom up is the positive z direction, the plumber is going down. So the z component of this 3-dimensional vector would be 10 meters going straight down. Right? And for our components, that's really all we need. So we have a 3-dimensional vector, got an x component of 50, a y component minus 25, and then if you can imagine, it's almost like it's going, downstairs 10 meters, right? So this vector is actually pointed kind of down, like that. Right? Okay, well, things get a little complicated now because the problem asks for what is the magnitude or length of this vector. And to figure out the magnitude or length of this vector, we're going to have to look at 2 different triangles here. All right? So the first triangle I'm going to look at is this triangle right here. All right? So I'm going to take this triangle and draw it over here. And I'm just going to think of it as a straight triangle, not even thinking about vectors here. I'm going to call this just dx, dy, and dxy. Okay? So I'm looking at this little triangle here. Notice that dxy here is really not the vector I'm looking for. It's, part of it, but it's not it completely. So if I were to say here what is angle theta and what is the length of dxy here, all right, you guys could do that, right? You would say, okay, the length of dxy here is equal to the square root of dx squared plus dy squared, right? Just good old Pythagorean theorem here, right? So if I plug that in here, I would get the square root of 25 squared plus minus, I keep on 50, that's a 50, minus 25 squared, and I would get the length of dxy is 55.9 meters. Now notice this is not the overall length of the displacement vector, all right? It's part of it. So now, to really find the overall length of the vector, I'm going to have to draw a new triangle. And this is going to be a really bad drawing here, but I want you to imagine this here and then going straight down into the paper 10 meters, okay? And looking at this triangle right here. So I'm going to call this dxy. I'm going to call this dz. And then really, this here, dxyz, is really the overall length of the vector that we want, okay? And I'm going to call this little angle in here alpha, all right? That's alpha, and this is theta. You can think of alpha in there as kind of like the angle below the horizon that this vector would be sunk down into, okay? Well, let's calculate what this dxy, the length of dxyz would be. And this is the overall length of vector d. Well, it would be the square root of dxy squared. Well, what is dxy squared? Well, dxy squared is really this squared, which is this squared, which is dx squared plus dy squared. All right? Did we get that, right? This squared is really this squared, which means get rid of the square root. So I just have that plus dz squared. All right? So we see that a length of a three-dimensional vector is really just the x component squared plus the y component squared plus the z component squared. So this is kind of like three-dimensional Pythagorean. All right? And this would be equal to the square root of 50 squared plus negative 25 squared plus minus 10. Am I running off the paper? Squared, right? Which would be the square root of, pardon me here, this is all equal to 57 meters. All right, so the overall length of vector d is 57 meters, and I got this by doing this squared plus this squared plus this squared. All right, so that's this side of this triangle here, which takes into account all three dimensions here. All right. Okay, overall length of vector d, or the plumber's overall displacement. All right. Now, we need to find some angles here, all right? Let's first find this angle theta here, all right? So let's find this angle theta here. Theta would be the inverse tangent of dx over dy, all right? So that would be, or pardon me, dy over dx, opposite over adjacent. And that would be 25 over 50. Okay? So that theta there is 27 degrees. All right? So 27 degrees is theta right there. Now, if we wanted to find alpha here, all right, alpha would be the inverse tangent of dz over dxyz. Okay, which is the inverse tangent of 10 over 55 point, pardon me, 10 over 57. Pardon me, 10 over 57. All right. So that turns out to be just 10 degrees. All right. So let's see if we can wrap all this up. And kind of get you an answer here. So the answer to this problem looks like this. All right. Instead of taking time to write this out here, I'm just going to write it out kind of like this. Okay. So the overall plumber's displacement vector D has a magnitude of 57 meters. Right. So that's this guy here. And it points in a direction 27 degrees. So we solved for theta here, and this angle theta was 27 degrees. 27 degrees south of east. Notice here, this is east, so this angle theta would be south of east, right? And 10 degrees below the horizontal. So if you were looking straight, if you were looking straight horizontally this way, your eyes would have to go down 10 degrees to see where the plumber is in the basement working on the pipes there. All right? All right? So, 57 meters, the plumber's displacement vector, 27 degrees south of east, and 10 degrees below the horizontal. So to totally describe a vector in 3 dimensions, we need a magnitude and 2 different angles. All right, well, nice job, AP Physics students. That was our first walk into 3 dimensions, and you guys did a really nice job. And because of that, you guys get a good joke here, all right? So, our joke of the day goes like this, all right? It's a chemistry joke. You ready? All right, so 2 chemists walk into a bar, right? The first chemist says to the bartender, "Pardon me, I would like some H2O." All right? And the second chemist says, "Oh, that sounds good, bartender. I'll have some H2O2. And then the second chemist dies. Get it? Because the second chemist drank H2O2, or hydrogen peroxide, which is a strong oxidizer and would kill you if you drank, a lot of it. So, all right, nice work, AP Physics students. We'll see you tomorrow.